Hello, my name is Jafar. As Steve said, I'm a lead software engineer working for Rare Game Studios. We are part of Microsoft. And today I'm going to talk about Rare's journey in adopting continuous delivery for our latest title called Sea of Thieves. Could you raise your hand if you work in games industry? Great. Just a few of you. So I'm going to talk about traditional development process in making games. Games are developed traditionally using waterfall process. There are three main phases. The first one is prototyping or pre-production, where small team start the project. They try to come up with a story, define what the game is about, and at the same time trying to prove the technologies and come up with a plan for the whole project. And we make some demos, and then we show the demo to business and marketing, and when we get the funding and green light, that's when we go into production phase. That's where team size increases significantly, and we have a lot of features being developed at the same time. The main focus is to develop just features at this stage. And then this can last about a year and a half, sometimes up to 2 years. And we go into the next phase, which is bug fixing phase. That's where we are faced with a deadline that we can't really move. We have to release the game by a certain date. And at the same time, we face a mountain of bugs, maybe about 10,000 bugs, and we have about 3 months to fix all of them. So it is a very stressful situation. There are a lot of bugs. People work crazy hours. They make a lot of sacrifices. They crunch. It is very stressful, and we try to do everything we can desperately to make sure we can meet the date. Games are monolithic applications, and they are mainly developed in C++. Between 300 to 500 people are involved when making AAA video games. And it can take up to 3 years, sometimes a bit longer, sometimes a bit less. And especially in the last phase, we heavily rely on manual testing to make sure we can find the bugs and catch them and fix them. And usually it's one big release, like what we've heard from other speakers earlier on. It's big bang release, huge celebration, follows by a handful of updates. And the team, at that point, move on to the next project. Nobody's worried about maintainability or having to worry about maintaining the code base. Could you raise your hand if you know about Sea of Thieves, if you've heard about it or you played the game? Okay, great. More than what I was expecting. By the way, has any of you actually played the game? Okay. So Sea of Thieves is our latest title, and it's a multiplayer cooperative adventure game where there is no predefined story. There are emergent stories that appear as a result of simple mechanics in the game. You form a crew, it could be with your friends or with strangers, and you go on an adventure. For this game, we decided to develop this game as a service, and comparing this to traditional model, as opposed to waiting for 3 years, develop all the features and release them at the end, we're supposed to deliver it way earlier and then get some feedback from our players and evolve the game and develop the game from the feedback from our community and our players. So far, we've done over 150 releases to our technical alpha audience. 150 releases might not sound too much to some of you. Some of you might be doing 150 releases in a week, even. But for games, that's quite a lot. And in fact, on Xbox platform, we have done by far most number of releases. I'll talk about this later on, but we had to have some conversation with the certification team to change their approach to accommodate this. And by the way, the game is going live today. So if you've done a good job in adopting continuous delivery, I think I get to finish my talk. Otherwise, I have to go and patch the build. So we'll see how it goes. Now I'm going to talk about why we decided to change our approach and adopt continuous delivery. As I mentioned, we decided to change our business model. We wanted to sustainably deliver new features over a long period of time. And we know that every time we want to release, people crunch. So if we didn't change anything, we would have had continuous crunch as opposed to continuous delivery. So we wanted to reduce the crunch and therefore have happier developers. We want to also get fast feedback from our players so we can evolve the game that is more fun for our players and have higher quality. In addition, we want to reduce the cost of having large manual testing. So what we found is as soon as we don't have manual testing anymore, nobody felt confident to go and make any changes to our code base. They all were worried they might cause some issues. And there's this concept of don't shake the jello, which is basically they're worried that if you shake it, everything's going to collapse. So all of the money spent on having manual testing is not an investment, because as soon as you don't have them, that's all gone. Next time, we're going to talk about the practices we've adopted over the years that helps us in adopting continuous delivery. We want to make sure our developers are responsible for the quality of their work. We didn't want them to rely on manual testing to catch bugs for us. And we found that it's very inefficient to test the game manually, as you would expect. It can take up to days to get some feedback on changes you've made, sometimes even longer than that. So our developers write automated tests. We have about 40,000 tests. We run about 4 million tests a day. 90% of these tests are unit tests written in C++, and the remaining 10% are larger tests, or end-to-end tests, performance tests, and memory tests. And when our developers fix bugs, they add regression tests to prove that they fixed the problem. We try to make sure our game is always shippable. If we prioritize fixing bugs and broken tests over developing any new features. And if our commit stage is broken or we can't ship the game because of some incidents, we lock the depot. And what we do is we try to identify the change that broke the build and back out the change. What we found is a lot less stressful for our developers if they come up with a fix in their own time. They don't have to worry about coming up with a fix when everybody is potentially blocked. As a result of this, the quality looks something similar to this, where the green line is here. So quality is always high at an acceptable level. That's why we can ship in between. And compared to traditional model where quality is generally very low, and it's only at the end of the project where quality level reaches an acceptable level. And that's one of the reasons you can't really ship the game during this stage, because oftentimes the game is crashes or different systems don't work well with each other. We work hard to make sure we work in small batches. We want to have as few number of changes in our build as possible. Because what we found, as I'm sure many of you have experienced, is when a build is broken and there's only a handful of changes in there, it's a lot easier to identify what causes the problem and back out the change, as opposed to when we're looking at a week worth of change. It's a lot more difficult. And on top of that, this many changes can be interacting badly with each other. So the risk increases exponentially as we have more changes in there. Here is like traditional branching strategy that we had and other game companies usually have. So we divide the game into different features, and we form teams around these features, and they go and develop their work in their own branches. And once they come finished, they merge back into Trunk. And at some point before the release, we create a QA branch to fix all the bugs, and then create a release branch to release from that. And once everything is done, we merge it back into Trunk. This has some obvious problems. We get painful merge conflicts. You have to bear in mind, for games, we still use centralized source control systems, like Perforce, for instance. And I've heard that, reading online, a lot of people talk about using Git potentially helps with merge conflicts. But you have to bear in mind that about 95% of the content of the game are binary files. And you can't really merge these files. These are like audio files, video files, like cutscenes, some textures, some models, animations, nav meshes. And these are stored as binary files. So if two people end up changing the same file in different branches, when you try to merge them, you have to override one or the other one. You can get semantic conflict. Oops, sorry. You can get semantic conflicts where, let's say, somebody goes and decides to split a function into two, and you're not going to know that your code is incomplete until later on when you get to QA branch and you find out that it's not working. And because you don't really get any feedback on your feature until it gets into QA branch, the feedback loop is extremely long. And on top of that, if we identify critical issues that requires us to fix, now we have to go and integrate that into many, many branches. So to make our life simpler, we decided to use trunk-based development. And all our features are simultaneously developed on the same branch in Trunk. And we release from Trunk as well. We don't create release branches. And one of the things that allows us to work this way is using feature toggles. We use compile time toggles. We decide at compile time what features we want to switch on, and we turn them on. And the features that are not toggled on, they're actually compiled out. We don't ship them to players. In addition to that, we use dynamic toggle, where we can choose to toggle the feature on or off for, let's say, a small number of players, because we want to prove out that the feature works, build confidence, or learn something about that feature. And we try to continuously improve our cycle time. Cycle time is a time it takes from somebody deciding to make a change until it goes through all our process and is released to production. And here are some of the benefits that we have found with improving cycle time. We get faster feedback loop, which leads to better quality because we can find problems sooner. Enables us to work in small batches and therefore reducing the risk. And allows us to respond quickly in case we find an incident or there's a problem in production, we can patch that earlier. Deployment pipeline is the implementation of our process from somebody making a change until it's out. And on this project, we decided to form a new team called Deployment Pipeline. And that's the team that I lead at Rare, and this is like a team of generalist engineers. And here are some of the things that we've done on this project. We developed our testing framework. We're responsible for the workflow from people making changes and get their changes in and testing. We look after our infrastructure and our pipeline. And we monitor and improve our cycle time. We developed a system to identify flaky tests. We implemented feature toggle in our code base. We continuously try to improve our build time and try to parallelize running tests across multiple machines to have shorter cycle time. We try to tackle technical debt. In the past, when we didn't tackle technical debt, a velocity looks something like this red line. By velocity, I mean the rate that we can deliver features. To begin with, when we start, the velocity might be high, but over time, that velocity goes down. It takes harder and harder to make changes. On the other hand, when we're tackling technical debt, to begin with, it might be slower, but as time goes by, that increases. And there's a point in time when these two lines crosses each other. And some people who argue against tackling technical debt, they would argue that the project would be done before these two line crosses. So there's no point trying to improve that. But what we found is unless your project's going to last only maybe 2 to 3 months, you're definitely going to cross this line. So it's well worth investing time addressing them. But at the same time, we don't have zero technical debt. Sometimes we intentionally accumulate technical debt because maybe we want to, let's say, release a feature to our players quickly. And then, but what we do is that once that's finished, we go back and pay that technical debt. We don't let it go out of hand. We try to do continuous improvement. I would argue that this is probably our most important practice. We're trying to build a learning organization. Different teams do regular retrospectives at Rare. Every time there's an incident, we try to do postmortems to understand why something's gone wrong and what we can learn from that. And more importantly, we try to allocate time for our developers to go and follow up on the actions we identify. Because what we found is if we just sit down and talk about these problems and don't actually take any actions, people would stop coming to our retrospectives or postmortems. So it's essential that we actually spend time fixing the problems. And throughout the project, we have evolved our process and principles. When we started this project, we didn't sit down and come up with these 8 practices. We read from other people's experience, what they have done, and we try to apply them to our own context. Try to see which one works for us, which one doesn't, and keep on doing the ones that make sense for us and keep doing it. And I would expect over the next couple of years, our process would evolve. Maybe we adopt some more practices, the ones that helps us and make sense for us. Now I'm going to talk about challenges in adopting continuous delivery. Adopting testing mindset was one of our big challenges to begin with. You have to bear in mind we come from a place where some of our developers would argue that they know their area so well that they can make changes without worrying of introducing new bugs. That might have been true maybe many years ago, but for this project we wanted to promote shared code ownership. We wanted everybody to feel confident that they can go and make changes to our code base. So it wasn't just enough that maybe a handful of developers can navigate the code base well. We want to make sure everybody can go and make changes under guards against them introducing any bugs. So what we did was we started with a small team who all believed in this idea. It was about 4 or 5 developers. And we gradually added more people to the team. And everybody who joined the team, they went through an onboarding process, including some test training. We didn't suddenly increase the number of members of the team. In addition, we had a separate prototype team. They were working on a different code base using even different game engine. Because what we found, again, from past experience, that often that prototype code end up being in the production with lower quality. So by actually having separate code base and using different engine, our developers had to go and re-implement the feature using different level of quality. Keeping commit stage short is another big challenge for us. And here are some of the lessons we've learned in trying to keep it short. We need to continuously improve our commit stage, otherwise it gets worse. Around the beginning of the project, we spent maybe about 3 months improving the commit stage to an acceptable level, and then we stopped. We moved on doing some other work. And what we found was, after a while, the commit stage was again where it was before. So therefore, we tried to continuously improve that. Sometimes some optimization can lead to more complicated systems. Therefore, whenever we're trying to assess a solution, when we try to optimize, we always try to see how we can choose a simpler option there that helps with overall simplicity of our system. We want to monitor stability and confidence in our pipeline as we optimize, because we don't want to have really fast commit stage that nobody trusts because we stopped running tests because they were taking too long. And we try to continuously identify unnecessary work and stop doing them. And here are some specific challenges with keeping the commit stage short. Compiling large C++ code base takes a very long time. It can take between 45 minutes to an hour sometimes to compile the whole code base, which you can't really afford to do in our commit stage. So what we do is we use distributed build systems that takes all the compile tasks and distribute them across many agents, and then bring back the result and the link on the machine. We work really hard to make sure our incremental build works well. That goes to what I was saying earlier about stop doing unnecessary work. Because let's say if we only change 5% of our code base, we don't need to rebuild 95% of the code base if they're not affected. So we spend a lot of time making sure incremental build works. And our build farm consists of about 150 powerful PCs that they all contribute to this. They are really beastie. As much as we like, we can't afford to run all our 40,000 tests in our commit stage. So we wanted to make sure we identify and prioritize our most valuable tests. And to begin with, what we did was we prioritized running the tests that were failing more often. And the tests that were not failing that often, we run them less regularly. But there was some obvious problems with this. If there was an area of the code base that was stable and nobody was changing them, we stopped running those tests. But as soon as somebody started to make changes in that area, they didn't know until later on, after the commit stage, in the later stage of our pipeline, that they have broken the build. So we decided to change this and improve it. So we came up with a system that creates a map between test and code. It runs each test and records what code files it touches. Creates a map between them, and then when it looks at the build and see what code files in there, it looks at the map and identify the tests that are covering those code files, and then only run those tests. Game packages are huge, about 100 to 150 gigabyte. And we may not need that 150 gigabyte package to run unit tests, but still they are part of our pipeline that we need to make sure that, like, let's say like performance tests, we want to run some performance tests in our commit stage, and we need to have this 150 gigabyte package available for us. So obviously having fast network connection helps. But on top of that, our build agents keep a local cache. So if they downloaded the build to run a job as part of our pipeline, and they need to run another job on the same chain, they don't have to go and re-download the build. They can use their own local cache. And on top of that, our build agents can serve artifacts to each other, so they don't have to all go to the central repository to download the build. Flaky Tests is another big problem for us, especially when we started, we didn't know how to write good tests. So a lot of tests that we wrote at the beginning were flaky, and they were failing a lot. So, and what we found now is actually having fewer tests that are more deterministic is much better than having lots of tests that are flaky. And we don't want to let these flaky tests to infect our pipeline, otherwise nobody trusts our pipeline. So what we do is we try to identify and quarantine these flaky tests. We either fix them and move them out, or if they're not valuable or it's not worth fixing them, we just delete them. And here are some of the causes of flaky tests for us. For instance, using random waits. Let's say sleep for 8 seconds. This was a common pattern we used for testing asynchronous behaviors. because we don't do, it's quite hard to do mocking in a lot of the engine that we use. So let's say a server wants a client, so it waits for a client, launches a client and wants to wait to check if the client joins the server. So it was waiting for, let's say, 5 seconds. And that might have been okay until we added more stuff to the game, which took longer to load. Therefore, that 5 seconds sometimes was not enough. So sometimes it was taking slightly longer than 5 seconds, and therefore the test was failing. We had some other tests that were not isolated. So they might pass or fail depending on what tests ran before. And if they change some states that these new tests, these other tests depended on, they could just randomly fail. On top of that, relying on some external dependencies, let's say some remote services. Again, because we didn't mock these external dependencies well enough, so sometimes that service might go down and some of our tests might randomly fail. Now, here are the challenges in actually releasing weekly with confidence for us. As I mentioned, game package is about 100 to 150 gigabyte. So we want to make sure when we patch the game for our players, the download size is actually quite small. Because releasing games and patching them is very similar to mobile applications. Unlike some websites where the update is seamless to players, players actually have to go and download the update. And if every time they want to play the game, they have to go and download, let's say, 20 gigabyte, they would stop playing our game. So we do everything we can to make sure this patch size is as small as possible. We want to make sure we minimize impact of something going wrong when we release, because we kind of expect something to go wrong as much as we try to prevent it. And to give you an example, let's say one of our services is down in the game, which means people cannot buy or sell items in the game. We don't want the game to crash if somebody goes into a shop. Instead, it would be much better if, let's say, we put a sign on the shop and says shopkeeper is away, come back later. So people can carry on playing the game, but they can't buy or sell items. We want to make sure we can identify issues, and so thanks to fast commit stage, we can then respond quickly to incidents. And finally, the certification process. Platform holders like Xbox, they have a certification team and a certification process, and their job is to protect their platform. They want to make sure the developers are not necessarily releasing features or some content that are not acceptable for that platform. And in the past projects, it could take up to a week, sometimes even up to 2 weeks for that certification process to finish. Therefore, our release could be bound by that time. We can't go any faster than that. So what we did for this project was we did a lot of conversation with the certification team. We did a lot of collaboration, and they evolved their process. As opposed to trying to prevent a lot of things, they kind of trusted us to do a good job, but at the same time, they were monitoring some key metrics in retail and production. Let's say crash rate as an example. As long as crash rate was below an agreed level, then they were fine. They kept trusting us, and we could keep releasing. And the idea then was, as soon as this key metric maybe suddenly changes, they can then jump in and have a conversation and understand what has gone wrong. We got to a point now where from the time we have a build until it's available for our players to play is about 6 hours. That's much improvement compared to 2 weeks that we had before. To summarize, here are some of the principles that we are trying to practice. We try to work in small batches to reduce the risk. We want to make sure we can release regularly and safely so we can learn faster and have better quality game. We prepared for things to go wrong, therefore we want to make sure we have fast response time. We try to continuously improve and learn and be better every day. But I have to mention the reality is a bit messy. So everything I mentioned here, we try to do as much as possible. There are some occasions that we have to kind of divert from doing them. Like I mentioned, for instance, trunk-based development, 90% of us doing that, but we have one special team that they keep using feature branches, but the idea then is that they integrate back into trunk every day or two. So it's not like feature branches that they go away for like months and then bring it back. But they decided to use it this way, but we have an agreement that, for instance, they integrate back. Another example was prioritizing fixing bugs over features. There has been some occasions when we intentionally didn't fix some bugs because we wanted to, again, go maybe deliver some features because we wanted to learn faster, but as soon as that was done, we went back and fixed all of those bugs. I also wanted to mention 2 books that have been very influential. Continuous Delivery by Jez Humble and Dave Farley is here. That have been very influential on me, so thank you, Dave, for a great book. And also The Goal by Goldratt. It's an amazing book, especially if you try to identify bottleneck in your process, trying to improve your pipeline. I guess I am still here, so I haven't been paid to go and fix a build or anything, so I guess this is kind of a sign that adopting continuous delivery helps. Jez Humble has a continuous delivery test, which says if you can release the game whilst you are in a beach having a cocktail, that means that you're doing a good job. And I'm not on a beach having a cocktail, but I'm here and giving you a talk, which is more exciting. So thank you for your time.